In the previous class, what we saw that we worked with the multilinear regression, okay? We had multiple features, variables, and we associated to each feature a coefficient, okay? This coefficient measures the association between the feature and the outcome, okay? What if we want to decide which features are more important for my outcome, okay? We can use shrinkage methods for this. These are very used in biological data, okay? Companies use this a lot, universities. This is very interesting. So what these methods do, they constrain, or we say they regularize the coefficients, okay? This means that they shrink the coefficients towards zero, okay? If we shrink the coefficients towards zero, that means we are saying, look, model, the coefficients that are closer to zero means that the corresponding variable are not so significant for the outcome, okay? And this reduces the variance of our model, okay? What is the variance? The variance says to me the complexity of my model. Look at this graph, okay? I have an error here and the complexity of our model here. So the higher the variance, the lower is my bias. The variance is related to how complex my model is. The more variables I have, okay, the more my model tends to memorize the data instead of learning the data. So I don't have a model with a very high variance. I have a model with a good trade-off between bias and variance. If I have a model with a very low variance and a very high bias, I have a model that doesn't learn not even the data I'm using to fit the model. If I have a model with a very high variance, a very complex model with too many variables, okay, and a very low bias, that means I have a model that is memorizing my data. So I have to find this point in the trade-off bias variance where I have a model that gives me the lowest error as possible. Okay, because if the variance starts to increase and the bias to decrease, the error starts to increase. If otherwise I have a very low variance and a very high bias, the error starts to increase again. So I need a model that's not so complex, but also not very, very no complex, okay?
Just to make sure I understood this, so I have my data, it gave me a model. This shrinkage method is something that is going to take my model and give me a new model.
No, it's the same. You can say it's a new model. If you consider a model as being a set of variables related to a data, then yes, then the method is going to give you a new model because it's going to drop some of the variables.
Yeah, it is the same kind of model, but with dropping some of the estimates.
And this is important. It's important to note that we are going to work with two methods here. The rigid regression is a very used method. It shrinks the coefficients towards zero, but the coefficients will never be zero. They will be very close to zero, but in the end, you will still have a model with all the variables. Then you can look at the model and say, these ones are more important than these ones, okay? But the variables are all there. If you use the lasso, then lasso will shrink the coefficients towards zero, and at some point, the coefficients will be equal to zero. Then you can use lasso to select variables. Okay, so lasso really drops variables from your model, while ridge no. And how do we do that? We just get our models that we know already, okay? Our least squares fitting, we know how to compute it, right? And what we do is we add a regularization term, okay? So for example, in the ridge regression, this is the regularization term. We just get the square of all the coefficients, okay? And sum all of them. And this term here, okay? This term here, it wages how much I'm going to penalize my terms. So the higher is this value here, the higher will be the penalization, and the higher, the more faster, I mean, I will shrink all the coefficients to 0. Okay? So you see, it's just the error I already know how to compute plus this term. Okay? Yes. So this is a tuning parameter, okay? We seek for the coefficients here that lead to this small error here, okay? The second term, the shrinkage term, or shrinkage penalty, okay, is small when the coefficients are closer to 0, okay? So the second term has the effect of shrinking the estimates towards 0. We're going to see that the higher this guy here, more we shrink the coefficients towards 0. So to find the correct value for this penalization tuning parameter here, it's not an easy task. What we do is that we test in a grid search, we test for many of these parameters, okay, in an experiment, and we then select the parameter that leads to the best model. Okay? Questions? Okay, so as I already said, so this tuning parameter here controls the relative impact of these two terms, okay, on the regression coefficient estimates, on the coefficients I am estimating here. So when this guy is 0, there is no effect on the penalization term. If this is 0, all this term is going to be 0, and we have the multiple linear regression as we are the same way we already know, right? However, as this term here increases and it tends to infinite, so the impact of the penalization grows, and the coefficients will approach 0. Okay? Okay, it's easy to understand because we are adding a term that's actually increasing our error, right? So the higher this guy here, the higher is the summation that's going to increase our error. So if you want to minimize the error, so we want if we want to minimize the error and we are increasing the summation, so our model will seek to find coefficients that tend to be smaller. Okay? Okay, good. It stopped working. So this is what happens. So as I increase here the tuning parameter, okay, the coefficients tend to go to 0. Sometimes they tend to increase, but at the end they tend to go to 0. So I'm shrinking the coefficients, okay? So here I'm seeing the coefficients. So it's easy to see that when this term is 0, okay, my model is reduced to the common linear model. Okay, so how can I find this guy? Well, I have to make an experiment with many of them to evaluate which model is going to be the best model, okay? So at this point, for example, I have a model with most of the coefficients. I don't know, take for example this point. I'm not going to be able to draw a straight line here, but you understand, right? If I get this point here, okay, I have a model where most of the variables, the coefficients associated with the variables, most of these coefficients, they tend to 0. So I have a less complex model, let's say. Okay, so I have to evaluate many values for the tuning parameter.
Could you please explain again the lambda and how it acts directly on the coefficients?
How what? How
It acts on the coefficients, like when you're talking about the lambda, if increases.
Yeah, because we want to minimize everything here, right?
Yes.
Okay, we want to minimize. So if I increase this term, okay, this tends to be higher, right? Okay, but if I want to minimize this, so the coefficients here have to be minimal.
Okay.
Okay? If I want to decrease the value, the coefficients have to go towards a minimum value, because if they are very high, I'm going to increase a lot the term, because I increased a lot this guy here. But as I decrease this term, as a decrease here, then the effect of having these coefficients going to 0 is lower. Okay, I can keep those coefficients more or less, not so high, but also not very, very small, okay? Because this coefficient here is very small, so the effect of having huge coefficients will not have a big impact on the error.
Okay, I got it. I think that's
It's okay? Is it okay?
When we talk about coefficients going to 0, the idea that we must have, at the end, we must have at least one coefficient that doesn't go to 0. Now we must have at least one variable that can explain the model. So when we are forcing these guys to go to 0, it means that we are like cutting variables, like, oh, I know that this one, it's not,
Yeah,
this kind of
that's the
thing.
idea.
So at the end, if we start with 100 variables, at the end, like the problem that we did before lunch, the program just said to us, oh, you have 50 variables that are redundant. I don't recall the number. During this process, we would be cutting those 50 variables, something like that.
Yes, we'll be cutting one by one. But have in mind that with this formulation, you actually don't cut, because the coefficients will tend to be close to 0. They will be very, very small, near to 0, but they will never be 0. Okay, so you can evaluate the importance of the variables, but they will never be associated to a value equal to 0. Okay?
And I understood that the lambda is this tuning parameter, but what defines it, the lambda?
What defines this value?
Yes.
So this is a difficult task. We don't know how to define a good value. We have to make an experiment with many values, and then we can evaluate the resulting model, for example, in a validation data set, or even in the training data set, and then we get the best model, which means that the best model will correspond, the best model I mean in terms of accuracy, for example. So the best model will correspond to the best value of the tuning parameter. Then I can get the best tuning parameter and use to predict a new value.
I guess what I still don't understand is, like, the point of this procedure is not to find what are the most relevant variables, right? Because here, when lambda equals 0, we can see already that there are some variables here that are contributing not so much, those gray variables, and then there are the other ones which seem to have a larger impact, right? So this is something that we can see from the start. So what is this doing actually?
No, it's different, because as the coefficients tend to 0, okay, for example, here, all these coefficients here, so all these lines here are coefficients associated to a variable. So you can see that at this point here, the more important variables for the model are this one, 1, 2, 3, 4. Okay, you cannot do that in the simple linear regression because you are not making any variable associated to a coefficient that's going towards 0. In the beginning, okay, this graph doesn't help a lot, okay, because you have many variables here that are close to 0. I got your point. But in a practice example, you are going to have most of the variables here, they are going to be they're not going to be close to 0, most of the coefficients, okay? They're going to be values, very high values here. You understand?
Yeah, and then you can see which ones go faster to 0.
Yeah, yeah, that's the idea.
Perfect.
But you don't know the exactly good value for the tuning parameter. So you have to, for example, perform a grid search to find the best parameter.
Is it possible to consider different values of lambda for each parameter? I mean...
Different values of lambda for each parameter?
Or why is the only one affect all
No,
the
I don't know such model. I don't know. I just don't this model. Well, the ridge regression that I know is just this model. What you can do is add another penalization term here. Okay, another value that's going to be a different letter, a different Greek letter, for example, a different value. And then you are going to add another penalization term, okay, with a different purpose, for example, shrinking the coefficients exactly towards 0, but they're going to be equal to 0 at the end. Then you have a trade-off between a penalty parameter that shrinks the coefficients to 0, but they will never be 0, and another penalty parameter that really puts your coefficients equal to 0. This you can have, but exactly one penalty parameter to each one of the coefficients, no, not exactly. Well, what we are doing here is that if you separate this, of course, this is a constant, this can be put here. You have at the end one associated to each coefficient, but it's one constant, right? Good? Nice. Oh, it doesn't change. Okay. And see, this graph shows that trade-off bias variance. So the advantage of ridge regression compared to the common least squares, okay, is rooted in this concept of the bias variance trade-off. So in the beginning, this theoretically is what we are going to find, okay? In the beginning, okay, you have here the tuning parameter equals to 0. So in the beginning, you have the normal least square linear regression, okay? You have the normal linear regression. So as the coefficients are being shrinked towards 0, the variance of your model is reducing, okay? Because the complexity of the model is reducing. Okay, as you put your coefficients towards 0, then you are saying, look, this parameter here has a very low association with the outcome. Okay, if it has a very low association with the outcome, then it will contribute very little to the outcome. So my model is being less complex because the number of variables that are really, really important are decreasing. So the variance is decreasing, and the error tends to decrease as well, okay? Until a point that, okay, if I continue shrinking the coefficients, I will get to a point where I will have no coefficient at all. Okay, then my model will be reduced only to the intercept. Okay, reducing the model to the intercept is the same as saying, look, take the average of the outcome and this will be the prediction. Okay, so this is a model that has a very, very high bias and no variance at all. So it's a terrible model. The error is very high. So we need to find a trade-off between the bias and variance using the penalization term. And to get a good penalization term, we have to find a good value here for our tuning parameter. And this is the task that's not so simple. We have to perform a grid search, okay? Question?
I'm trying to understand why should the mean square error go down? Because in the first in the image that you showed us with the dots and the lines, for me it seems that the mean square error in this more complex model would be lower because it predicts better the data. But the problem would be that's overfitted, and if you try to predict data that you didn't use in the training, then the error would be higher. Yes.
Yeah, that's a very good question. Okay, if I get the data that I'm using to train the model, yes, the mean square error will be very, very low. And then you are going to say, oh, this is the best model with all the variables. But this is an error, because you don't want the model that's going to be the best one in the training data. You want the model that's going to be the best one in data that the model didn't see to train. Okay, so if you get this model will have a terrible performance in the test data, the real world data. Okay, and if you get this model is terrible in the real world data and even in the data you are using to training it, to induce it, the model. Okay.
Okay. So someone has another mic. Because okay, no, it came back. Okay. And about the coefficients, so you are not this regression, bridge regression is not actually dropping the coefficients, right? You are like reducing all of them continuously to zero.
Yeah, I mean reducing the importance. The coefficients are very, very close to zero, but they are never zero.
Okay.
Yeah. Okay. No, that's a very good question. So this is one thing you have to have in mind always when working with machine learning. Okay, a good machine learning model is the one that has generalization ability. What that means? It has to be good in predicting new data. Okay, a very good example is span filter. Okay, your span filter was trained with millions of emails already labeled as span and not span. Okay, so in practice you have a function that separates points from span to not span. Okay, and the variables are the words that appear in the emails. So you have a good span filter is the one that is good in predicting different emails, new emails that are not here in this training data set. So this figure tells exactly that. You have a model that doesn't have a very high variance, because if your span filter has a very high variance, it will not be able to correctly classify new emails. Okay? Yeah. Oh, yes. Oh. Oh, I was here. So very good. So this is ridge regression. Okay. Now the lasso regression is a good model, okay, if I want to select features. Because as I was saying, the lasso regression includes all the predictors, okay, in the final model. They may be very close to zero, but they are never zero. So this penalty term here will shrink all the coefficients toward zero, but will not set any one of them exactly to zero, okay? Okay, unless of course it's equal infinite, but will never set equal infinite, okay? So this gives me a problem, that's interpretation problem. So suppose I have a problem with, I don't know, hundreds or thousands of variables. Okay? So to interpret that model, it will be more difficult than interpreting a model where I actually drop some variables. Okay? So we wish to build a model that include, at the end of the model, we will include just the predictors that are considered really very important for the outcome. Okay? So actually, we are going to be selecting features. And to do that, we just change here, we just change the parameter, okay? Instead of calculating the square, we just take the absolute value. Okay? This will make that the error surface really touch zero, the points of zero. So we just replace. We just replace here by the norm. So now we have what we call the L1 penalty. Lasso is the L1 penalty instead of L2 penalty. So this is the L2 penalty, and this is the L1 penalty, because we are calculating the L1 norm of the vector of the coefficients, okay? So if beta here, okay, is the vector of coefficients, so the norm of the vector will be just the summation of the absolute values of each of the parameters, right? Each of the coefficients. So we're just summing the coefficients. Okay? And this will actually make the coefficients go exactly towards zero as the tuning parameter goes to a higher, very big value. Okay?
But not necessarily infinity, right? That's the difference.
Yeah, not necessarily infinity. Yeah, but infinity is, will never work with an infinity number. But
Yep.
they will go to zero depending on the value you put here. They will be equal zero.
Oh, different from the lasso, right? Because the lasso,
No, different from the ridge.
the ridge, yeah.
Yeah.
Okay. Thanks.
Different from the region. Good. Yeah, here. So this penalty here has the effect of forcing some of the coefficients to be exactly equal to zero when the tuning parameter is sufficiently large, okay? So because of some of the coefficients will be equal zero, the associated variables will be dropped from the model, okay? So because of that, the models that are generated are usually much easier to interpret than the ones produced by the ridge regression. Okay. See, this is another graph. So here, the coefficients will actually tend to zero. Okay, looking at the graph, it seems that it's the same thing as the ridge. But because the coefficients in ridge, they are very, very close to zero. But here they are actually zero. Okay? So as the value here increases, the modules, the coefficients will be shrinked exactly to zero. Questions up to now?
But lasso also make effect in all the variables or using?
All the variables.
No.
Okay?
Okay.
It's all the variables here. It's the same thing as ridge, but we are just changing here. Okay? So some of the coefficients will be zero. Okay, let's put this in some code. Okay. So see what we are going to do here. We are going to read the SNP data we have just created in the previous, okay, before lunch, okay? I'm just going to read this guy here. You already have it. Good, good. Okay. Here, I'm just doing the same thing I've done before, okay? I'm just finding the more correlated data here and removing them. Okay, it's the same thing. See? So I have a SNP data filtered now. Okay, now we have to use this package. Okay, because with this package, we can implement Ridge and Lasso. Okay, this package has a parameter alpha. If alpha is equal 0, then we are using Ridge. If alpha equals 1, then we are fitting a Lasso model. Good, so I will, okay, here. I just loaded the library. Now I'm going to make a little bit different modification here in our data. So I have to use this model matrix here to model my data frame to pre-process it in a format that the package reads, okay? So I'm getting my target here. I'm saying, okay, model matrix, okay, take SNP data filtered, okay, except here, oh no, sorry, take my SNP data filter here, okay, and model as a matrix all my data, and remember that the target is the target variable, the outcome that I want, okay? And then I'm removing here the -1 because in the first column there's some information that I don't want, like the name of the row, something like that. Okay? So X, and maybe, if I'm not wrong, actually, the first column here holds the target. That's why I remove it. Yeah, that's it. Okay? So X will have just the variables, and then SNPs will Y will have the SNPs in the target position. So the targets will be in Y and data will be in X. Okay, now I have separated the variables from the target, okay? And now I can fit a ridge regression model, okay? So remember I said that to find a very good value for the tuning parameter is not an easy task, okay? So what I'm going to do here is that I'm going to define here a grid, okay, a vector of many values, grid. Okay, very high values until low values. Okay, it's just a vector. If I plot this guy here, look, I have all the values that I'm going to test when inducing my model. Okay. Okay. I will just use this library here because maybe I will need this, okay? Now I'm going to use here the ridge regression model. So I'm going to induce a model, okay, passing the variables, the target, and this will be a ridge regression model, okay? And as lambda, the parameter, okay, the tuning parameter, I will pass my grid. Okay, so he will induce a ridge model with all the lambda values that are in my vector grid. Here. Okay, degrees of freedom are the number of variables, okay? And these are all the lambda values here. Okay, and the standard deviation for all the values. Okay. Nice. But the important thing is that having our model, okay, we can plot here the values of the coefficients, okay, against the normalization of the norm. Okay. Actually, I will plot against the lambda because the L1 norm, I don't think it's adequate here. Okay, so I have the lambda. So as the logarithm of the lambda increases, okay, or as lambda increases, the coefficients are going being shrinked towards 0. It seems to be 0, but they are actually never 0, are very, very, very close to 0. Our value is very close to 0. Okay, so at this point, for example, I have some variables that I can consider more important, but I'm not selecting variables, okay, because I don't have actually these variables associated to 0 coefficients. Is it okay? Okay, yeah, this is the same. Okay. So what I'm going to do here, let's see here. Associated to each value, I have a value of regression coefficients, okay? Associated to each value of lambda, I have a vector with coefficients, okay? So what I can do here, for example, is that I can get a given lambda, for example, I can get the coefficients for a given lambda, for example, the lambda 50, okay? Let me see here. See, I have a given lambda, okay? This is a given value of lambda. I have the coefficients associated with this lambda, okay? Then I can get, for example, the square of the coefficients, okay? But it's important that given a position of the 50th coefficient here, I get all the coefficients that are associated to the 50th lambda, 50th value of lambda, okay? Okay, yeah, that's it here. And what we can do here, given see how interesting. Given a given, I don't know, a given value of lambda, I can predict the coefficients, okay? So I can say, for example, give me the coefficients for lambda equal 50. Then I can predict the values for lambda equal 50, or for lambda equal to 1, I don't know, okay? For lambda equal 1000. And you see that it tends, as I increase the value of lambda, as I told you, the value of the coefficients tend to 0. You see? But they will never be 0. They will be very, very low values, but they will never be 0. Okay. Let's do an experiment here. Let's take our data, okay? And let's split our data in training and test data, okay? So what I'm going here is that I am getting a sample of numbers, okay? Yeah, from the set of numbers that goes from 1 to the number of instances I have in my data set, so 541 instances, okay? I'm going to take a sample that's the size of 1/30 of all my instances, and this will be the test instances, okay? And then the train indexes, the indexes for the training instances will be exactly the ones that are not the test instances, okay? See? Then the training data will be my variables indexed by the index train. The target variables will be the target variable indexed by the index of the training, and it's the same thing for the test. Okay, so I randomly set here a train and test data sets. Now, I'm going to fit a rich regression model, okay, using the training set, okay, passing the targets of the training set, it's a rich regression model, and lambda will be the grid of values that I'm going to test for all the lambdas. And here, I'm just doing a prediction here with lambda equal 4, okay, in the test data set. Then I'm getting the test data prediction and comparing it with the test here, and calculating the mean square error. Okay, so I fit here a model with many values of lambda. Then I'm just predicting the values using the model I just fitted here, but using a given value of lambda, I don't know, 4. And comparing the predicted values with the true values. Here, okay. So, predictions, true value. For the test data set, so these are values that were not seen on the training data. Okay, and here I have, here, the mean square error. Okay, so remember this value. So instead of, see now, I just got an arbitrary value for lambda, right? I just made a prediction with lambda equals to 4. But instead of choosing an arbitrary value for lambda, it would be much better to get the lambda that led to the best model. Okay, so what we are going to do here is to use this function CV glimnet, okay? So this function, okay, what it is going to do, it's going to perform a 10-fold cross-validation in order to get the best argument. What's a 10-fold cross-validation? Who knows? A 10-fold cross-validation is an experiment where, I'm going to draw this because this is important. Okay. Suppose I have my data here. Okay, this is my data. Okay, a 10-fold cross-validation splits this data in 10 folds. So I'm going to split here. I'm going to call it k-fold, okay? So k-fold. So it splits my data in k subsets. Because I don't want to draw 10 here. So 1, 2, 3, 4, 5, 6. So I have here a 6-fold cross-validation. So what it does, in a first interaction, okay, these 5 folds are used by training, as training. What happened? Oh, okay. So in the first interaction, so for you guys that didn't see, so suppose this is my data, my training data, okay? A k-fold cross-validation divides my data in k subsets. So k here is equal to 6. 1, 2, 3, 4, 5, 6. So in the first, so now I'm going to perform 6 training test experiments. Okay? So in the first experiment, these 5 folds are used as training, and this is used as test. Okay? And then I compute, so I train the model in this partition here, composed of 5 subsets. and compute the evaluation measure, for example, an accuracy and a precision in the test set. Okay? So now, okay, this was one interaction. Okay? In the next interaction, okay, now let's see how I'm going to draw here, this one. In the next interaction, these guys here plus this guy here is going to be the train. And this one here will be the test. See? So these guys are now, these guys together with this one are train, and this is going to be test. In the next interaction, this guy, this guy, this guy, and these two will be train, and this one will be test. So I will perform k experiments every time k minus 1 subsets will be train, and the remaining will be test, okay? With this, I can validate more statistically my experiment, because I'm performing many experiments randomly choosing train test partitions. I can perform, I don't know, L times K fold, okay, to make many repetitions of experiments. And then at the end, I will have many values for my many evaluations on my test data sets, and then I average it. And then I have an average performance over many testing subsets that were randomly generated. You got it? So this function here, how can I go back here?
I have a question.
Oh, a question.
How do you select which K to use? Like a 6-fold, a 10-fold?
Commonly we use tenfold.
But is
Yeah.
there some
I believe that after many years performing experiments, 10 is a value that's more commonly used, okay? So 10 is a very good value, but in some experiments they use 10 plus 10. So it's 10 times tenfold, you know? You perform the tenfold cross-validation 10 times and average the results. So if your algorithm involves many probabilistic procedures, then it's good to make a 10 times tenfold, okay? But otherwise, usually if you perform a tenfold cross-validation, then it's a good experiment. Okay? Thank you. Okay, so that's nice. So this function, this CV, again, will perform a tenfold cross-validation, okay? If I'm not wrong, for each value, for many values of lambda, okay, for different values of lambda. And I don't have to pass here the values of lambda, okay? It chooses automatically many values, like a grid of many lambdas, and perform this cross-validation experiment using different lambdas, and then returns to me the best lambda, the one that corresponds to the best model. Okay. So what I'm going to do here, I'm going to make it separate for you to see, guys. I'm going to execute this here. Figure margin is too large. What? Ah, okay. I didn't get it. What do you say? Here? Ah, you know R much more than me. Thank you. Okay, so I'm going to do this and this. No, there is no plot. Oh, here's my, no. Where's my plot? No, but, oh, no. Oh, yes, because I'm executing here, right? But I wanted to execute here outside. Yeah, but you are right. I'm going to use this one here. It's easier. Yeah, so that's my plot. You know, these are the degrees of freedom, right? And so, as lambda increases, you know, you have a mean square error and a standard deviation for each value of lambda. So here you can see that the best value is probably here, because you have the lowest mean square error. You got it? So after running this experiment, I can get the best lambda. Okay? Here, this is the best value of lambda. I'm going to execute everything here. Okay? And now you see it changed. I'm going to execute again. It changed again. You know why it's changing?
Every time you run, it partitions the data differently.
Yes. Okay. If I want the same, I'll probably have to set a seed here. Set seed, I don't know, 1, 2, 3, 4. Let's see if it. Yeah, see? Exactly. Okay. Very good. Now having the best lambda induced in the training data, okay, now I can get this best lambda and use it in my model to predict using new data. Okay, so actually, remember, when I am getting, remember that, when I am getting my best lambda, okay, when I am getting my best lambda, see here, I don't know, I'm going to draw something here. So y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus blah, 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 plus beta p x p. Okay? So, when I'm getting the best value for lambda and applying and making a prediction using the best value for lambda, what I'm actually doing is saying, look, get the model, okay, whose lambda that I am choosing led to given values, okay, not considering the intercept, okay, but led to given values of beta 1, beta 2, and beta p. And some of these values will be very close to 0, but not 0. Very close to 0. So the best lambda led to a model, okay, where we could make some coefficients go very close to 0 and say, look, these coefficients, they participate in the model. They contribute to the final prediction. But they contribute very little. The ones that have the higher coefficients, they contribute a lot. Okay? So the complexity of the model, I mean, in terms of interpretation, is still high, because all the variables participate in the model. But I can look at the variable and say, oh, this one contributes a lot. This one contributes very few, very little, okay? Is it okay? Good. What should I press here?
This one, with only the computer.
Thank you. So this is nice. So look, so I'm getting the model. I'm passing the best lambda as argument and the new data. And I am predicting here. I'm getting the prediction and comparing here with the true values and calculating the error. Okay, so the error here, where's the error? Was 31, right? If I compare to the error I had there, was 34. So the error with the best lambda was lower than the error with a, I don't know, an arbitrary lambda. Is it okay? Good. Oh, no, here. Okay. And here, okay, yes, here. And now what I can do is get my model, okay. It doesn't have to be out here. I'll get the same guy here. My model here, my RegPred. Actually, it's not out here, okay? It's my RegPred. I don't have to consider this, okay? I can get my model, RegPred, no, Reg model. RegMod. I can get my model, okay, and get the coefficients associated to the best value of lambda. See? And here are the coefficients that are associated to the best value of lambda. You see that you have small coefficients, like, I don't know, 0.5, minus 0.1, but they are never 0. None of them, okay? Okay, now, suppose I want to perform variable selection. Okay, now, okay, I don't want a model that gives me all the variables. I want a model that really puts the coefficients equal to 0 because I want to select variables. So let's use the lasso, okay? For lasso, I put alpha equals to 1. And I'm going to pass the grid. Okay, now here I have many values of lambda, okay. And this degrees of freedom actually gives me the number of variables that are being used. Remember, if I get here, let's go back here to the lasso, no, sorry, to the reg. When here, reg, you know that reg, look at here. Okay, these are the values of lambda, and degrees of freedom is always equal to 50. So I'm using all the 50 variables every time. Okay, doesn't matter the value of lambda. I'm using all the 50 variables. They're all part of the model. Now here, when I am inducing, oh, I'm lost. Here, when I am inducing the lasso model, for some values of lambda, I don't have any variable at all because all the coefficients were shrinked towards 0. They are exactly equal 0. So for this model, they are not good models because I'm reducing, okay, my model to the intercept. But for some values of lambda, see that I start having some variables participating of the model. Nice. Until there is a point where when lambda is equal to, actually equals to 0, I think it's very close to 0 here, okay? But I have some variables that start not participating in the model. And what I can do is plot here the lasso here. And what I'm doing here is taking the L1 norm. So I'm plotting the values of the coefficients against that parameter, okay, L1 norm. Okay, the vector, the L1 norm of the vector of coefficients, okay? And we can see that the coefficients tend to increase, okay, as the norm increases, okay, as the norm decreases. Because if the norm decreases, that means that the value of the coefficients are decreasing. So you see that the coefficients are decreasing. Okay, and here I'm plotting against the value of lambda. Okay, and actually will be the values equal to 0 for given values of lambda. Sum of the coefficients will be actually equal to 0. Okay. Okay, nice. So, depending on the choice of lambda, sum of the coefficients will be exactly equal to 0, okay, and some not. So we are going to do the same thing we did with ridge regression. We are going to perform a cross-validation experiment. Okay, so I'm getting my training data, the labels. Okay, I'm doing a a lasso regression now in a cross-validation experiment. And I'm going to plot here, see, the cross-validation experiment. So the value of the error as lambda increases. So at this point, more or less, I have the lowest error, so I have the corresponding best value of lambda. Okay, now I can get the best lambda. This is the best lambda. Again, the other best lambda. Okay, I can put a set seed here. To get always the same lambda. Good, now I can make predictions. So I'm going to get test data, okay, and make predictions using the model in the best value of lambda. Okay, and you see that I have an even smaller value of mean square error, okay? But I have an advantage when using lasso over ridge. That's variable selection. So we have to perform here the variable selection, okay? So I have here the best lambda, okay? So what I'm going to do here? I'm going to perform here. No, let me get my X-train here. X-train again. Here, X-train. Yeah, I'm performing here the grid. No, that's not what I want. Yeah, I'm performing the experiment again, actually. I'm doing experiment again here. Okay, so I'm running, but I want exponent, sorry guys. Yeah, exponent train. Y train and okay, train. Yeah, what I'm doing here is actually performing here again an experiment with all the lambda variables, then getting the best one and predicting, okay, the values of the coefficients, okay? And see, here are the coefficients. And you know that now we can see that many of the coefficients are actually equal to 0. And some of the coefficients are not equal to 0. And I'm actually selecting variables. Okay? So I can get the lasso coefficients where lasso coefficients are different from 0. See? Now I'm getting, look. These are the variables that I can consider truly important for my model. So from 100 variables, I selected only how many of them? Oh, no, lasso coefficient. Eu. I'm not good with technology, sorry. Yeah. So I'm getting the best variables here, and I'm getting the length of the best variables. See? Yeah, I'm going to print the best variables. Come on, print best var. See, so I have, these are the best variables, and I have actually 9 because the intercept here is counting, so intercept doesn't count. 9 variables from 50, right? Good? Yeah, we can, here I'm doing again the same experiment, okay, dividing my data in training and test data, okay, I already did that. Comparing the prediction, yeah, this was done before. Okay, do you have questions? No, any questions? Well, if you have no questions, then we are going to start a new topic. Just 1 minute. I think I'll have to disconnect here for just 1 minute. Okay.
I have a question actually.
Yes, you can ask.
When performing lasso and ridge, just because we in lasso exclude some variables, does this mean that we can get the same results in terms of predictions? Or, because maybe I was thinking that if ridge considers more things, maybe the predictions would be better, but computationally more expensive. But can they get the same performance? Or not?
They can get the same performance, but with lasso you have the advantage of having a more interpretable model.
Okay.
Yeah, you know, that's the big difference. But what we really want is to have a more interpretable model together with a good prediction performance. If you have, if we have a, I don't know, a good interpretable model, but the performance is not good, then it doesn't, it's not okay, okay?
In terms of computation, of computational demands, we can say that because ridge considers all variables, it would be more expensive to run it, or not necessarily?
I don't think it will be not. It will be very almost imperceptible, because the time you spend, the most of the time you spend on machine learning is on training the model. Okay, not on making predictions. To make predictions is easy, but to induce the model is more time consuming. And both in ridge and lasso, you are like testing all the variables, okay? Of course, ridge, I believe it's going to be a little bit slower because you are going to have all the variables in the model every time for all values of lambda. Okay, and lasso will be a little bit faster. But it's not, I mean, much perceptible that. More questions?
I guess more of a conceptual thing, right? I guess many of us learn these kinds of linear models and things like that, but not really in the context of machine learning, right? So, like looking at this as a learning task, what are we assuming in a sense about what we're trying to teach, right? Because we're assuming, of course, that there is a kind of linear response. So what kind of task, for instance, would this be representing? What would be an application of this kind of thing? Or
Well, we can think about many applications. For example, suppose you have a plant. Whoa. Suppose you have a plant. I don't know. You have to predict the productivity of a plant. For example, we have some applications that we work together with Embrapa, for example, where we want to predict the productivity of rice, or some quality of rice, predict the durability, I mean, how hard is the grain, for example, if the grain doesn't break, if the grain doesn't break easily. So we want to predict all these kind of things, given a quality of rice. So the features are SNPs, okay? We can fit a linear model to find what are the SNPs more related to the desired characteristic. That can be productivity, durability, and any other characteristic, okay? Yeah, this is one application, but we can have many other applications, like we can, yeah, for, sugar cane, for example, there are many companies that they were agricultural companies, that they want to predict the durability and the productivity of the sugar cane, a given species. So they want to find the SNPs that are more related to this kind of durability or characteristic of the rain, because if they know that, they can produce varieties of rice that are more resistant to some weather, for example. Another application, for example, we can find, transposable elements. Yeah, we can try to find what are the different classes of transposable elements, for example, that are more related to the productivity of some grains, like, for example, sugarcane. In sugarcane, there's a lot of transposable elements. Okay, so in those GWAS, in GWAS procedures, you find all of these molecular markers and genomic characteristics, like DNA characteristics, like transposable elements, small no-coding RNAs. You can extract features from these guys and try to infer what are the features that are more important for a given test, for a given characteristic you want to predict, okay? So there are many applications, okay? And this kind of technique you saw here, like ridge and lasso regression, they are very used for many companies that work with bioinformatics, for example. They use a lot. Mm-hmm.
My question is more like to this part of model selection and things of the like, because the way I was introduced to this topic, especially in modeling selection, was like in ecology, and you have some models, and you have a few, not in this case, but like you have hundreds or thousands of predictive variables, but you have some, and then people use things like the negative log likelihood to select the best model. But it's the first time I'm seeing this approach, and I'd like to know how do these two things relate when people use one over the other, if they are related at all.
Yeah, that depends on the outcome. Okay, that depends on the target you are predicting. Like you can use the log likelihood or another error function. I don't remember to say you exactly when to use one or another, okay? But I mean, at the end, you want to minimize an error function, Okay, you want to minimize a criterion, né, to find the best model. And this criterion can depend on your application. Like for example, you may want to minimize not only a prediction performance, like the error, but also a prediction performance together with having a model that has less variables. So you have both, you want to have both things, okay? So it really depends on the application, but it is related, okay? When you are minimizing like log likelihood, you are minimizing a function that is related to your data to find the best model. It is related. More questions? Okay, so we have a few minutes. I want just to start a different topic. It is still machine learning, but it is one thing that maybe you are not familiar with. Okay. Okay, let me get here. Oh, first, I think I will use, because we have another 10 minutes, I think it's better if I use the board, okay? Can you change there, please? Can you change there? I think I'm going to use the board because it's easier in these last 10 minutes, just to introduce you. Do you know decision trees? No? Yes? No? No, that's good because you're going to learn. Haha. Okay. Now, suppose you have, okay, a bunch of data. I don't know. Let me say. So suppose you have, okay, that's going to be a table, okay, an attribute value table, just for you to think, okay? Okay, so this is my target. This is my target. This is variable 1, variable 2, 3, 4, 5, 6, okay? And this is sample 1, sample 2, sample 3. Sample n. So you have many samples and some variables and some targets, okay? And now let's suppose now these targets are categorical. I don't know, let's think about the biological data. I don't know, let's say. Suppose I want to classify, I don't know, small no coding RNA, okay? And let's say that this small no coding RNA, let's say it belongs to two classes, two plausible classes, A and B. Okay? How do you think we could try to separate this subset of data in two subsets of data? Here is the outcome, okay? Here is A, B, I don't know. How could we think in choosing, suppose I want to take this data and break it in two. What would be a good strategy? Breaking it in two, okay, in order to try to separate data from one to data from B. What do you think would be a good strategy?
Can you explain the setup again? What is the S's are going to be the things we want to classify?
Yes, the S's are the sample.
They are the samples and these V's?
Examples. And V's are the variables. So V's, for example, are the SNPs.
Okay,
are the variables. And these are sequences, you know. For example, small no coding RNA sequences.
And A and B are not known at the start. right? We
No,
don't
A
know
and,
how
A
to-
and B, A and B are known because I need a training data. So this is my
okay.
training data.
Okay, okay, okay.
Okay, I have a training data. I want to induce a model here, okay, that the objective of the model is separate data from A to data from B. Okay. So I get a sequence, I extracted some features and put all the features here. So what do you think would be a good strategy to get this data and make a first split on the data in order to maximize the subsets, okay, in order to make the subsets be pure, like more data that belongs to A in one side and more data that belongs to B in another side. Do you know what I mean? What do you think would be a good strategy?
I mean, we could pick a variable and pick the mean of this variable, and whatever is below the mean, we call it A, and whatever is above, we call it B. Could be a first step.
Yeah, so you are going to make this for all the variables. You get a variable, you calculate the mean of the variable, the mean, okay? So the mean of, I don't know, V1. So then you get a sample. If the value of V1 for that sample, I don't know, is smaller than the mean, so it belongs to A, goes to one side. If it's higher, goes to another side. And how do you know that this will going to separate? Okay, do you think the mean is going to be a good strategy? I don't know. Do you think that in the data, if you look at the data, okay, all the variable for all the values, all the samples that for that variable have a value lower than the mean belong to A, higher than the mean belong to B? Yeah, already. You have the target.
I would say that having this parameter to this line, this threshold to divide, it's nice, but I guess actually the program will give us what these values is. Now, I don't know how to separate everyone. We would need the machine to tell us what are the thresholds. I don't know how.
Yeah, I mean, the mean is like a guess. Getting the mean will be more or less getting the, if I get the linear model, remove all the variables, for example, I say, predict the mean, for example. The mean, I think it's a kick. We have another question. Do you?
Okay. I was thinking about maybe seeing what the A guys and the B guys has in common. So maybe splitting in groups and then seeing what values they share. But I still don't know if it is a good idea. I don't know.
What if, oh no, let her talk first.
Yes, okay.
Let her say first.
For me, it's kind of confusing to see those B's because, for example, if you put like a name of the B's, let's say that B1 is equal to the sequence length of the samples, that could be like a decision for, you know what, small non-coding RNAs actually have a sequence length in average. And if the samples agrees with that category, I consider as a small non-coding RNAs. And if the sequences are larger than the, you know, like the length that I know that the majority of small non-coding RNAs have, well, I consider like different category or something like that. Because first I need to specify like what are the variables that I am measured? Because if I see just like that, it's kind of difficult, right?
Yeah, so we are getting close. So suppose, okay, you have a variable that's the length of the sequence, as you said. So that's going to be one variable, the length of the sequence. So what if for each variable we see, based on the outcome, how this variable separates data? So we are going to measure this that you said. Okay. We are going to get, let's suppose that V1 is sequence length. Okay. So we will have to find a cut. We are going to have to test all different cuts here in the sequence length, because we have many sequence lengths here, right? So we are going to have to test many different cuts here. For each cut, we are going to have to test, okay, if the sequence has a sequence length, for each sample, we are going to compare V1 with the cut. If the length of the sequence is lower than V1, go to the left. If it's higher or equal, go to the right. Then we do this for all the sequence based on one division. For example here, one division. Okay, and then we look at the subsets that were formed, okay? Let me draw it here. So, V1. V1 divides the data into two subsets, depending on the length of the sequence. So we will have to look at these subsets and see how many B's and R's are here, and how many B's and R's are here. You know? And then we are going to look at these subsets and say, look, there are much more A's here than B. There are much more B's here than A's. And then we start wondering, oh, this can be a good variable because it separates very good the sample, the initial sample. But we have to perform this for all separations of sequence length. Okay? Yeah, we have to perform many cuts here. The cuts are performed here are going to be tests here. And then each test will produce subsets. And then I'm going to see which cut produces the best separation. Did you get it? But now we have to do this for all the other variables as well. Okay? So this is actually what a decision tree does. It gets one variable and sees, oh, let's see how that variable separates data. And then it sees here how are the subsets that were constructed. Okay, and now it says there is a calculation that's performed here that I'm not to tell you now. Statistics perform this for us, but say, oh, V1 gets a score 1. Now let's do the same for V2, okay? Let's get V2. Let's see how V2 separates data. Okay, now V2 can be, for example, I don't know, molecular weight, for example. Okay, I'm guessing here, molecular weight. Suppose V2 is molecular weight. Then I'm going to get many separations here, make many tests for molecular weight to see how V2 separates data. Okay, now suppose that V2, instead of being a numeric variable, suppose it is a categorical variable. You know, suppose it has, I don't know, three values, P1, P2, and P3. Then I have to perform a test to see how the variable v2 divides my data based on the values p1, p2, and p3. I don't have to perform many cuts anymore because it is a categorical data. You see what I mean? No? If I have a variable v1, and this variable v1 is a numeric variable, it has a range of values, I have to make many cuts here to be used as tests to see how these tests divide the data. Okay? Suppose I had many values here, 1, 2, 3, 4, 5, 6, 7. The first test is V1 is higher or less than 1. The second test is V1 is higher or less than 2, higher or less than 3, higher or less than 4, higher or less than 5. I have to make all these tests and see which one's the best one that leads to the best division of my data. However, if V1 has categorical attributes, I don't know, P1, P2, P3, P1, P2, only P1, P2, and P3, categorical values, then I don't have to make all these divisions. I already have the test performed here. For all the samples, I only have to check if the value of V2 is equal P1, P2, or P3. Okay, get the value of, okay, now suppose V2 is a categorical variable. Then I get V2, and I check if, for all the samples, if the value of P2 is equal, value of V2 is equal P1, P2, and P3, and check how the value of this variable, okay, divides data. Then I can check, oh, this variable seems good, because I don't know, all the values here are A. But if V2 is equal P, I have more or less the same amount of data from A and from B. Oh, so this is not a good variable, a good separation. You know, so a decision tree makes exactly this. It chooses a variable to be put in the root of the tree. It's a test in my data. Then, given the separations this test performs, it chooses another variable to separate the data that was already separated here. So this variable separates here more data. So now, given these data that are here, I have to choose other variables that make good separations on this data. Okay? Until I find subsets that I call pure. Subsets that are formed only by data belonging to A or belonging to P. And in the end, I have a tree. Okay, if V1 is equal to A and V2 is equal to, I don't know, if V2 is higher or equal to a given numeric value, then classify in class A. See? We are going to do this tomorrow, step by step, okay? In a very good example, then we are going to perform an experiment in R.